red, this dark red. Okay. So, okay. We know that this is an aldehyde based on this functional group. So we have a carbonyl group and we have a hydrogen attached to it. So I know that that is an aldehyde, right? So the first thing I'm going to do is identify my functional group. So I'm like, okay, we have an aldehyde here, right? So this is my aldehyde group. So I'm like, immediately I'm starting to think now, what kind of reactions do aldehydes undergo, right? That's my first thing that I'm thinking in my head. Now I'm trying to remember these aldehydes reaction. All right. So let's go to B, right, for this transition. So when I look at this compound in B, right, I can see that there is a OH that's been added to this carbon, which is the same carbonyl carbon, right? So I see that they added a OH group in there. So I see that OH group here. And I also see that a cyanide ion, right, has been added to that carbon as well. So there are two things that have been added here. And this is, what would this be, guys? What is this, an electrophile or a nucleophile? What is this? Cyanide ion. It's negatively charged, so it's a what? Nucleophile or an electrophile? Per our discussion last time. All right, so it's a nucleophile, and we see that it's being added to this carbon, right? So it's added here. So we say what's taking place from a reaction standpoint is a nucleophilic addition, right? So we're adding these nucleophiles there. So it's a nucleophilic addition. And so it's just the reagent that will be needed to create this particular kind of structure would be HCN or hydrogen cyanide. And just to like let you guys know what's happening from a mechanism standpoint is that what happens is the OH, so let's talk about the OH part first. So what happens is, let me just show you that real quick so you see how those two come in there. So what happens, guys, is that this CO, so let me just put C here so you know there's a C here. It's a polar bond, right? So I can get a CO like this, and this is my partial positive center, and this is my partially negative center, the O portion, right? So what happens is that this oxygen is gonna take the two electrons from this bond to itself, right? And then the CN, which is this nucleophile, is gonna come in and attack this. It's nuclear loving, so it loves positive things, right? So the electrons from the nitrogen portion of that cyanide is really what's coming in here and coming to form a bond now with this carbon. Again, this is our carbon that's here. And so you see that that's added here, right? Now remember that this oxygen here had taken two of the electrons from here, right? And so what's gonna happen now is that this oxygen will end up having, so let me draw over here. So we'll have C. So we have the CN that has come bonded in. So this is the CN portion of it. And then we have the C here, and then we have the O. And because the O pulled two of the electrons to itself, it ended up being like this, where we have a negative charge on it, right? And so what's gonna happen is the H that's in the solution is gonna then take these electrons. So there's a H plus, right? Because this is essentially H plus CN minus, right? Really, that's what hydrogen cyanide is H plus CN, right? So the H plus that's coming from that CN is gonna form a bond with the oxygen. And so that's how we end up with this now being the carbon be modified to create this OH, and the CN gets added onto it as well, and then everything else is the same, right? Do you guys see that? So we still have our hydrogen that was here, right? They show it up there now, and then we have CH2 2. And then, of course, we have our CH3 remaining as well, because only the functional group is reacting, right? So come again, let's recap again. This carbonyl carbon has a partial positive charge on it. And so this is going to be a partial negative charge on the oxygen. So that's what I've shown over here. The nucleophile is going to come in and attack this partially positive carbon center, because nucleophiles love positive things. It's coming in, attacking this, and so it's going to be able to form a bond with this carbon, right? That's this carbon, and so we get the CN being attached. And so we see the CN being attached right here. And then this OH is going to take the electrons onto itself, one from the bond, a pair from the bond, and then we're going to end up getting our CN that was previously attached just now here. And then the O is going to have a net negative charge on it because it had gained 2 electrons. And then now that those electrons are going to be attracted to the H plus from the HCN that's in solution, right? And so we form a OH bond here, and that's how this OH comes into being. Is that clear to you guys? Is that clear, guys?
This you can run that through one more time from the aldehyde to part 2.
Okay. Acidify. Let me just write this real quick. The reagent. Let me just write this real quick and then I'll run through it again. So acidified, what we use is acidified NaCN, right? So this is like on site, they're gonna make the HCN. So what happens is that the reaction is actually gonna be to produce the HCN, that is, guys, is gonna be NaCN plus H plus. And that's what's going to get us our HCN, which is then added nucleophilically to the carbonyl. So let me write HCN is going to be there. And then Na plus. So if you write this, you should be good in terms of marks for this reagent. So Na plus is going to be there. Okay. So now let's go back up here to recap. So this is our aldehyde. We see this functional group. So this is our aldehyde, right? It goes to this. When it reacts with acidified NaCN, which yields HCN, right? And so what's happening is that the CN is acting as a nucleophile and being added nucleophilically to this carbon that's this carbonyl carbon. And then the OH is also coming into play as well because of the how the nucleophile does its thing, right? So the nucleophile, which is CN or cyanide ion, comes in, right, and attacks this the positive end of this carbonyl bond because it's C and O, right? So we know oxygen is more electronegative. So generally speaking, it would polarize this way, and this part would have a partial positive charge, the carbon, and this part would have a partially negative charge. So that's why we write partial plus, partial minus, right? So when the cyanide comes in and goes like this, donate its electron to this carbon center, what it's effectively doing is forming a single bond between the carbon and the cyanide. So that's what we see here, a single bond between the carbon and the cyanide. So that's what this first step is, right? So this is part 1. And then part 2 now, what's going to happen is that you have this double bond, right? And what happens is the oxygen now is going to take 2, right, from here, 2 electrons from this double bond onto itself. And so it ends up having a net negative charge on it, right? And so that way it can attract the hydrogen ion that's in solution that's coming from the HCN to itself. And you end up with an OH group being here. So that's how this OH came from. This oxygen that took away these electrons from the double bond, the carbonyl bond, is able to then have a net negative charge, and then it attracts this H plus ion that's floating around in the solution from the HCN, and then it forms OH, and then we just end up having this structure. This is a complete new structure. Does that make sense?
Yes, miss.
All right, perfect. All right, so the second step, what's happening here? We're going from an aldehyde functional group, and from we see our COOH, we know that this is a what? Carboxylic acid, right? So that's a carboxylic acid. So how do I go from an aldehyde to a carboxylic acid? What reagents do I need?
Potassium dichromate.
All right. So let me scroll up a little bit here. Okay, so I need potassium dichromate. What conditions do I want to do that reaction under?
Acidic.
Okay, so acidified potassium dichromate or potassium manganate, either one works, right? Let me go back up here and write it here. So let me erase this cyanide stuff first, so I have more space here. So let me erase this stuff. And then I'm gonna write now that for this transition, we need acidified. KMNO4 or chromate, dichromate, so K2Cr2O7, right? So that's potassium permanganate, potassium dichromate. So we want that acidified, we want it in excess. So let me write excess acidified KMNO4 or K2Cr2O7, and we're gonna heat under reflux, right? Heat under reflux. Okay, so that's what should go here. So how we go from A to C. Okay, guys? So that's what we put in this section here for part 2. Are we good on that?
Yes, Miss.
All right. So let's see what the rest of the questions ask. So let me clear that whole thing and go down. So draw the displayed structures and provide names for each of the following compounds, compound D and compound E. So we have to come up with what the structure at D would be and what the structure at E would be, and then name them. And that's 2 marks each, right? So let's go back up and look at D, and let's look at E, right? Do any of you guys want to volunteer to draw what you got for D and what you got for E? Desiree or Hubert? How are you guys with this part?
Miss, I can try to draw D.
Okay, so go ahead and draw D for me. So go ahead and draw D for me and then name it, and then I'll have Desiree do E. Tell me what's gonna come from the D, okay? So go ahead and show me what you got for your structure at D, Hubert, and then we'll go from there.
Yeah, miss. I think it's ethanol chloride.
Okay. So what happened to the rest of the molecule, Hubert? So we had two carbons over here and then the CO. What happened to this part? I think you missed off the CH2. That's supposed to be here, and then that would change the name, right?
Yes, miss, yes.
Yeah, so that would be propanoyl chloride instead of ethanoyl chloride, right?
Yes, miss.
Yeah. So just add on that for me and just change that name to propanol since there are 1, 2, 3 carbons, okay?
Yes, miss.
All right. So then now Desiree, going from here now, when we react the propanoyl chloride with ethanol, what are we gonna get at E? And do you want to go ahead and just draw that structure for me? Propanoyl chloride and ethanol are gonna give us what? What compound and what do we call it? All right, so that's propanyl chloride that we're gonna get in the for D, right? So that's correct. So that's what would be in here, right? And then now we're gonna react this with alcohol under these conditions, right? Triethylamine is this thing down here that we're combining. Those are our reaction conditions, and we're gonna get, what are we gonna get, Desiree? What are we gonna make? What kind of compound? What functional group?
It's an ester.
All right, so it's gonna be an ester, right? So go ahead and just draw that ester so we can see that structure. So I think you're missing the CH2 as well. Like, I think you're missing the CH2 beside the methyl group there. That's attached to the carbonyl. So remember that this is what we're starting with, right? This is our chain portion of the propanyl chloride, and then we have C double bond O, and then the alcohol is just gonna come in here to form the ester. So you're missing your CH2 here, right? Do you see that?
Yes, miss.
All right, that's perfect. So what do we call that molecule there, Sherry? How would we name it? All we have to do now is just name it. All right, so it's ethyl propanoate because the first part of the name comes from the ethanol, so it's ethyl, and then the last part is from the propanoid chloride portion, so that's ethyl propanoate. So that's correct. So now let us clear all of this and move on to the next part, which is asking us to consider the equation below, which shows the dissociation of chloroethanoic acid in water, right? So here we have our chloroethanoic acid. That's just an ethanoic acid that has been substituted with one chlorine, right, for one of the hydrogens. And we're dissolving that in water, so using water to dissociate it to get our H+ ion, right? And then what would this be, or what we call the conjugate base, right? So whatever remains. So this is what we get. So they're saying, okay, now write an expression for the Ka of chloroethanoic acid. So the Ka is the acid dissociation constant. It's the extent to which the chloroethanoic acid is ionized, right? When it's in water. So we would just write Ka is equal to the concentration of these ions that are formed. So CH2Cl minus times H+, right? The H+ concentration at equilibrium divided by what we started out with at equilibrium. What's the concentration now of our chloroethanoic acid at equilibrium? Are you guys good with writing Ka, expressions for Ka? Are you okay with this stuff?
Yes, but
Okay, and we
but how
don't.
come it's the H+ instead of H3O+?
Okay, so it's the same thing. So let me be consistent and write what they wrote. It's the same thing. Hydroxonium ion and H+, we can use them interchangeably. But let's be consistent with what they wrote. So let's write H3O+. So it's H3O+, it's the same thing. Hydroxonium ion. Okay, all right. So now write an expression to show how pKa is derived from Ka. So what is this formula relating these two things, guys? How do we relate pKa to Ka? How do we relate pKa to Ka? Anyone?
Got that one, yes.
What was that, Hubert?
I forgot that one, man.
Okay. Desiree, any idea?
No, miss.
Okay, so the pKa, guys, is just equal to the negative log, right? So negative log to the base 10 of Ka, right? So that's how we relate the two things. And what I will say here, since we're gonna do it in the subsequent questions, let me just say off the jump here, right? That because of this relationship, right? If I have a high, okay, let's start over here. If I have a strong acid, right? An acid that dissociates to a great extent when it's in water. If I have a strong acid, my Ka, so going back up here, my Ka is gonna be high, right? And my Ka is gonna be high if I have a strong acid, because it means that I'm gonna get a lot of these ions, right? I'm gonna get a lot of these ions relative to what I started with. So this number will be small and this top number will be big. And so my Ka will be high if I have a strong acid, right? So I have a strong acid, I have a high Ka. No, if I have a high Ka in here or a big number, right? And I take the negative log of a big number, I'm going to get a small pKa. I'm going to get a small number. If I log a big number, guys, I'm going to get a small number. If I log a big number, I'm going to get a small number. So if I have a high Ka, that means I'm going to have a low pKa. That's how that relationship works, right? And so what that means is that strong acids have a low pKa, and then by that same token, if I have a weaker acid, right, that weaker acid will be dissociated only to a small extent, and so I'll have a lower Ka, which means that I have a small amount of these dissociated ions at equilibrium. And because I have a low Ka, which is a small number here, if I take the negative log of a small number, I'm going to get a big number. So I'm going to have a high Ka for my weak acids, and my stronger acids will have a lower pKa. Do you guys follow that?
Yes, miss.
All right, so strong, just remember this. Strong acid, low pKa. Weak acids have a high pKa. Just remember that because it's important as we go forward, okay? All right. So let me clear that, right? And then move on down. All right. So we have our table 1 here, and table 1 shows the compounds and their pKa values, or we should fill in the blanks with their pKa values, right? And so what we have here, guys, is we have just your regular ethanoic acid, and then we start to substitute out the hydrogens with chlorine. So this one has 1 chlorine, so this is a monochloro, right? Monochloroethanoic acid, dichloroethanoic acid, and trichloroethanoic acid. So in this one, all the hydrogens from the methyl part that we started with ended up being substituted. So we went from CH3 to CCl3, COOH, right? And they're saying now, guys, that we have to complete table 1 by correctly inserting the pKa value of each compound from the following list of values. So they give you a list of values for pKa, and what we can notice immediately is that we have from a low pKa going all the way up to a high pKa of 4.7. So what we're really being asked to do is figure out, right, of all of these, figure out weakest and highest, and then assign pKa values based on that. Figure out weakest to highest, weakest to strongest acid, right? So we have to figure out how it goes, and then we will assign the pKa values on the basis of that. So let me just recap what I said earlier. I said low pKa. We're going to put our low pKa with our strongest acid. Because if you have a low pKa, you're a strong acid, right? All right. And so if you have the highest pKa value out of those that they gave us in that list, is gonna go with our weakest acid. So that's really what they're testing here. All right. But now what you have to do is when you look at all of these, which one is the weakest acid, which one is the strongest, and then you can assign pKa values based on that. Okay. So does anyone have any idea which one is the weakest, which one is the strongest, and how would you know? So after you assign it, you're gonna have to give reasons, right? So how would you assign these values and then give me your reasons why you're doing that? Okay, guys, any thoughts on that one?
So the first one I would put 2.86.
So you'd put that for ethanoic acid?
Yes, miss.
Why?
Miss, I don't know. Probably because it already readily give up any hydrogen to make it a proton donor. I don't know. I'm not sure.
Okay, so what you're doing is you're comparing it to all the other ones. So when you compare all of them together, would this be the weakest one? Or would this be the strongest one? So, okay, let me give you guys a hint, right? So you remember how last time we were talking about compounds that are electron withdrawing and compounds that are electron donating? That's the kind of reasoning that we have to use here to determine the strongest acid. So let me just draw the structure of, say, the one that's at the top. So this one, ethanoic acid, and let me draw the bottom one now. So I'm gonna write C, right? This is Cl, one Cl is here, a Cl is here, and then another Cl is down here. And then we're gonna have our C double bond O, O, H, right? Let me show that bond here as well, the OH bond in its entirety. So I'll just write OH. So that's our first compound. That's just our regular ethanoic acid up top. And then at the bottom, I have trichloroethanoic acid, right? And so the idea here is that, or the key knowledge really, is that chlorines are electron withdrawing. So they're going to pull away the charge from the carbon to themselves. So I draw arrow pointing towards the chlorine, draw arrow pointing towards the chlorine, and one pointing towards this chlorine. So they're pulling electrons to themselves. So Cl is what we call electron, right? Withdrawing, right? So our chlorine is gonna pull the charges to itself, or the electrons to itself. So what's gonna happen is that the net effect is that the carbon is gonna end up being really positive, right? Because we're pulling away the electrons from around it. So it's gonna end up being a positive center, right? And so because it's positive, right? Effectively, it's gonna kind of run off this hydrogen. This hydrogen is gonna be like, okay, I'm out. I am out of here because it's too positive here for me to stick around. So I'm gonna come off, and so you will end up getting your H+ ion. And we know that strong acids are proton donors, right? So this one is gonna kick off its hydrogen much more strongly than one that only has 2 chlorines in it, because imagine 3 chlorines pulling the electrons to itself versus 2. This is of course gonna be a stronger effect, right? And so this will be much more positive. And so this H+ will want to leave, this H will come off as H+, right? And acids are proton donors, right? That's what we define them. Acids are proton donors. So whichever one readily gives up its H+ is gonna be the strongest one. So this is our direction of strength then, right? The one that has the most chlorine is gonna be the strongest, right? And then the one that's at the top is gonna be the weakest. So is that clear?
Yes, miss.
All right, so in light of that now, I want you to tell me how the pKa values are gonna go now. So this is our weakest. The weakest one, weakest acid is gonna have the highest pKa. Remember this? Low pKa is for our strongest acid. So let's start with our low pKa for our strongest acid. So the lowest one would be 0.70. So I'm gonna put this here. This is my strongest acid, so it has the lowest pKa. And then this is my second strongest, so it has the second lowest pKa. This is my third strongest, so it's gonna have the third lowest pKa. Wait, so this is my third lowest pKa actually. So let me put, so this is my second lowest pKa is 1.48, and that's for this acid that's here. Then my third lowest pKa is 2.86, so I'm gonna put that one here. And then my highest pKa, right, is 4.76. Remember now, guys, high pKa corresponds to our weakest acid. Low pKa corresponds to our strongest acid. So do you guys get that?
Yes, miss.
Okay, so we've kind of just answered part 2 in part 1, and part 2 and part 1 all in one, right? So the reasons for assignment, can anybody recap? The reasons for assignment is what? How was I able to rank them the way that I did? Anybody wants to recap or tell me their understanding?
Increasing the number of chlorine and electron withdrawing on the atom.
Mm-hmm. All right, so this is what I wrote. So in a nutshell, this is how I would summarize it, and then you can always talk about, so that's how you're able to come up with this determination, right? So chlorine is an electron withdrawing group. More chlorine atoms means more electron withdrawing from the attached carbon atom. So that's this one. And as a result, the carbon gets a partial positive charge, and that just kind of feeds through the structure, the whole structure here, right? So what happens is that this hydrogen the attached hydrogen leaves or is donated more readily. And we know that strong acids are great proton donors, right? So trichloroethanoic acid, this one with the 3-chlorine will be our strongest acid, which then has the lowest pKa. And so we can rank accordingly. Okay, guys? So we can fill out the table in that order. Right? Is that crystal clear to you guys?
Yes, miss.
All right. So that's that. Bam. Right? So I'm gonna clear this now, clear all of this that we have here, and then move on to the next page. And on the next page now, they're saying, so that was for 5 marks, guys. So you see the level of detail. So filling out the table correctly is 4 marks, and giving the reason is 5 marks. So you have to make sure that you hit all the key points, right? Talking about the electron withdrawing and how that makes it a stronger acid, and then correlate the strength of the acid to the pKa. Those are your key points that you have to hit to get the 5 marks, okay?
Yes, miss.
Okay. All right, so let's talk about phenylamine now in a similar fashion that we just did for the for these compounds, right? So let's look at phenylamine now. It says account for the fact that the pKb, right? We know that amines are bases, so now we can speak of a pKb, right? And the pKb is just gonna be the negative log of the Kb, which is the base dissociation constant. So that's the extent to which the base dissociates in solutions, right? Do you guys follow that definition? It's the exact same thing as acid, but now for bases, okay? And we know that amines are bases, meaning that they are proton acceptors, right? So let's write that. Bases, we know that they are proton acceptors, right? And the acids are proton donors, and the bases are going to accept proton, right? So ultimately what we're looking for is it's going to be a stronger base if it can accept protons more readily. So we want to end up having a more negative center, right? So negative is going to be good for us because we want to attract a positive, right? Which is our proton. So we want to be able to accept our proton. So we want to be as negative as we can be, okay? So that's where we're going with this. So keep that in mind. Again, the Kb is the base dissociation constant. And if it's high, if the Kb is high, it means that we're gonna have a low Kb, pKb, right? And if the Kb is high, that just means that we have a strong base. And that would mean that we have a low pKb if we have a strong base. So let me just summarize that down here, just like I did for acids, right? So again, in the same fashion, low pKb corresponds to a strong base, right? And if we have a high pKb, right, we have a weak base, right? So effectively, what this question is saying is they're saying account for the fact that the pKb of phenylamine, which is this structure here, is greater, the pKb of this is greater than ethylamine, which is C. Right, so let me just put my H's for completeness here. Right? So we're comparing this, and we're saying the pKb for this one is much greater than this. So this has a higher pKb, which means that it is the weaker base of the two. Weaker base than our ethylamine. So they're saying, okay, account for that fact. right? The pKb of phenylamine is greater, which means that it's a weaker base than ethylamine. How do we account for that? And the key part here, guys, to zero in on is the fact that this group here, right, is a methyl group, right? And we might remember from the previous session that methyl groups are electron donating, right? Electron donating. So they're going to donate electrons to the nearby atoms, right? So methyl group is electron donating. And then, so it's going to donate. It's going to donate electrons to this nearby carbon. So we're going to end up with what? A negative center here, right? Negative center. The phenyl ring, so this ring here is actually electron withdrawing. So it's going to pull electrons to itself, right? So this is going to end up being more negative, and then up here now it's going to end up being positive because it's got this, the phenyl ring is going to withdraw the electrons to itself, leaving up here being net positive and down here being negative. And then over here, the methyl group is going to donate its electrons. So it's going to end up having a net positive here, but this carbon here is going to end up being negative, right? Which is going to in turn make this nitrogen more negative, to which the hydrogen is attached, right? All right. Do you guys follow that so far? So phenyl ring, let me write that here. Phenyl ring is electron withdrawing. Right? Do you guys follow me up to that point?
Yes, ma'am.
All right. So the net effect is that this ends up having a net positive charge up here. This has a net negative charge over here because the methyl group is donating. So remember what we said earlier about bases being proton acceptors, right? So protons are positive, as we said. So it's going to be attracted to whichever is more negative, right? And so because this nitrogen is more negative, right? Then hydrogen is going to be more attracted to over here than it would be to over here. And so hence, phenylamine ends up, what we see is that it's a weaker base. So it's less able to attract protons when compared to ethylamine, which has this negative center by virtue of this electron donating methyl being here, right? So because this is more negative, it's going to attract H plus to itself, because H plus is a positive charge attracted to a negative charge. Okay, guys, does that make sense to you guys?
Yes, miss.
If there are any questions that could clarify it any further for you, let me know, okay? But that's really what we're working with here. So when you're given these kinds of questions with pKa or pKbs, the first thing to remember is that a low pKa or a low pKb corresponds to a strong acid or a strong base. So then you can start to think, okay, what's attached? What is attached to the center that's going to be accepting protons or donating protons? And then you can be like, okay, this is a withdrawing group, so it's going to make here positive. This is a donating group, it's going to make here negative. And in the case of bases, we want to attract protons. So this wouldn't be so good at that. It would be repelled, right? Because protons are positive and we ended up with a positive here. And over here, it would be great for us because protons are positive and the donating group made this much more negative. So this is going to win. Okay, guys? Is that clear, Desiree?
Yes, miss.
Okay, so let's move on to this question about polymers. I'm going to have one of you guys take the lead on this one. Or I'll give one of you to do polymer P and one do polymer Q. So what we're doing is they're showing repeating units here of two polymers, polymer P and polymer Q. So this is just a repeat unit, right? And I want you guys to draw the structure of the monomer used to form polymer P. So I'm going to give Desiree, come up with the monomer that formed this. And then Hubert, I want you to come up with the monomers. I'm giving you a hint, the monomers that formed Q. Okay? Is that okay with you guys? Okay. So you guys just feel free to go ahead and draw it on my screen. Okay, so Desiree, this is correct, this is the correct monomer. So now, what type of polymerization is involved in converting this monomer into this polymer? What's the type of the all right, perfect. So that's addition polymerization, so that's correct. And then Hubert is drawing the monomers that were used to form polymer Q. That's our next question, so he's working on that. So Hubert, right away, what was the first thing that you noticed when you look at polymer Q? What was the first thing you noticed when you look at that repeat unit?
Another that, so this bond here repeated,
Yeah.
and then I noticed that it had a double bond here and here.
Okay, so where are those bonds coming from? Oh, so I guess my first question is, what functional group is present in this repeat unit? Like, what's the functional group that's present in the repeat unit?
I must have seen a carbonyl functional group, and I'm not sure what to call I forget what to call the double bond O.
Yeah, so the C
From
double bond
that O.
O, what will this be? This is an ester linkage, right?
Yeah.
Yeah, so we're forming a polyester, right? So that's the first thing that I want you to make note of, so that then that will help you in deciphering out what the monomer should be. So if this is an ester linkage, right, it means that it was formed from a diol, right, or a dialcohol and a diacid. So when you're drawing your structure, what I want to see is a diol and a diacid. And so because it's a polyester, and when we look on this structure, we see that we have this functional group here that's at play, right? Then we know right away that what kind of polymerization would it be, first of all. To form polymer Q from its monomers that you're going to draw for me, right? What kind of polymerization would we need to do? Because we're going to make an ester.
Condensation.
Condensation, that's perfect. And we're going to get water as a side product, right? So that's how we know it's condensation, because a water molecule gets condensed off when we form polyester, okay? So you are correct, that is condensation polymerization. But now I want you to break down that repeating unit into the monomers. And so as I said, the monomers would be a diol and a diacid. So let me help you with the diol part, and then I'll have you do the acid, okay? So
Yes,
to come up with the diol, right? This part that just has a O hanging out is what's coming from our diol. So this part, so here, right? And then here would be coming from our diol, right? And so then the rest of it would have been our diacid. So I'll just break it here, and I'd have H, so I'd have H, O, bam, H, CH3, and then this, HCH3 again, right? And then the O now, this O is also coming from the other part of the, makes it the diol, to make it the diol. So we get CH3, CH3, OH, OH, right? So that's my diol. So this is my diol, right? So this is kind of like ethane diol, right? 1,2-ethane diol is what this is. And then I want you to draw the diacid for me. Can you do that? The remainder of this repeating unit comes from the diacid. So can you just complete that for me and draw the diacid right here? So do you understand this part? The diol part, how we figure out the diol?
Yes, ma'am.
Okay, is this clear for you today, Shari?
Yes, miss.
Okay, so now Hubert is just gonna draw the diacid, which would have combined with the diol to give us our polyester repeating unit. Okay, so that's perfect, right? So that's kind of what? Ethane dioic acid, right?
Mhm.
Is that what it would be? Okay, so that's that. And then you name the type of polymerization, and that would be condensation. So that's correct. So let's move on. All right, so we did that part. Hubert just did this. All right, so let's talk about this part now. Can anybody tell me the answer for this? We have to identify a compound which in aqueous solution will break down polymer Q but not polymer P. So look at this one and tell me how you would actually break it down to come up with the monomers that we just spoke about that made them up, right? So we're gonna break down the polymer into its monomers that made it. So we're gonna have to hydrolyze Q. We want to break up Q, but leave P intact, right? So what can we use to hydrolyze polymer Q, but not touch polymer P? So we have to select a compound that can do that. So what would you guys use to do that? What would you use to hydrolyze an ester, guys? In the ordinary fashion, if it wasn't a polymer, how would you hydrolyze an ester into its constituent units? What would you use? What reagent would you use ordinarily? Are you guys still with me?
Yes, miss.
So how would you ordinarily hydrolyze an ester, Hubert?
Add OH minus ions or water.
Repeat what you just said.
Add OH minus ions or water.
All right, so what can we use? So we can use aqueous NaOH then, right? Aqueous, so we can use aqueous sodium hydroxide, right? So we can use aqueous NaOH to hydrolyze P, and that's not gonna affect polymer P, which is made up of an alkene, right? So this is not gonna affect it. So aqueous NaOH to hydrolyze polymer Q. Okay, so that's what we would do. Okay, guys, are we good on that? So this is an alkaline hydrolysis that we're doing here. Okay?
Yes, miss.
Okay.